aeronautics, as well as a master's in EE and a PhD in astronautics and aeronautics. For 21 years, he was in the United States Air Force, where he rose to rank of colonel, and he received numerous awards for his achievements in the United States Air Force. Finally, our final presenter and member of this panel is John Preston, at the far end on my left. He is the Director of Technology Licensing Office at MIT. He has a bachelor's in physics and an MBA, and prior to that, he was an Associate Director of the Technical Liaison Office at MIT. John has been a catalyst in establishing companies based upon exploiting, using, applying the technology that's been developed at MIT, and he has been involved in the founding of the American Superconductor Corporation that you've read about recently. Before coming here today, I did an informal survey of the venture capital field. Not everybody in the field was contacted, but I called firms around the country to get a feeling for what they are doing, what they're up to these days. And the conclusions of that horseback survey are that a few firms, and some of which you'll hear about today, have taken some action, have made investments, and we'll hear about those investments today. But most of the firms in the venture capital industry in this country are studying the field, studying with a lot of intensity, or are in the phase of planning to make some investments. So there's a lot happening right now. The investment strategies of these venture capital firms fall into three categories. One is what you might call the usual venture capital investments. Investments in companies by venture capitalists hoping to make those companies successful. The focus of those investments to date have been on companies that make equipment or offer supplies to do research in superconductivity, or companies in low temperature superconductivity, such as Eric's company or Carl's company, that would be able to capitalize on high temperature superconductor materials. There's also talk about making investments in companies that would perform research, perhaps government research, under contract and be contract research companies in this field. There's another class of investment that's being discussed these days, and we have at least one example, and maybe I should call that investments made on the Genentech model, after the company in the biotechnology field, where a company is formed that has a relationship with a university, where the university researchers contribute ideas to the company and they have partial ownership, where the university itself has some participation in the company, and that the focus of this company is to apply those research ideas to real products. The founding of the American Superconductivity Corporation, which will be described in some detail by John Preston, is an example of this kind of investment strategy, but there are others that are being developed and planned even as we speak. The third investment approach to this field that I've heard about in talking to people in it is the idea of corporate partnerships. Partnerships between large corporations that have resources with new enterprises, where you leverage the resources of the big corporation with the new company, or a cooperative research program along the model of MCC in the advanced computer business. Speaking to this kind of approach will be Paul Kaminski. His firm is involved in setting up these corporate partnership arrangements. The purpose of this session is to allow each of the panelists to describe their thoughts and experiences in this field, but the main value of the session is to be able to get your ideas, your questions, and use the panelists as a catalyst in order to have a workshop type discussion. And we'll go from this point to about 3 o'clock this afternoon with the combination of presentations and discussion. So with that, I'd like to call on Henry Kressel of Warwick Pincus to start us off and describe his experiences. Henry?
Thank you very much, Ed, and it's a pleasure for me to be here. And what I propose to do in the next few minutes is to give you a case history of the founding of Hypris, which is the one example in the last few years of a company devoted solely to superconducting electronics technology.
Microphone's on.
Warwick Pincus. It's dead. All right, this one better? Okay, great.
I guess I spoke so loud, nobody noticed.
Warwick Pincus was the lead investor in Hypris and has continued a very close interaction with that company. Other venture capital firms have also participated in the financing of Hypris. Before going into some details of how and why we helped found Hypris and how its strategy was developed and how decisions were made regarding programs and products, let me say a few words about Warwick Pincus, because I think it's really germane to the way we have handled that investment. Warwick Pincus is a large venture capital firm. We currently have $1.5 billion under management, and we provide a very diversified investment outlook with regard to the kinds of industries in which we invest, the size of the investment, and the stage of the company's maturity at the time what we do when we make an investment. Our companies are in electronics, advanced materials such as ceramics, biotechnology, medical services, communications, media such as newspapers and cable, retailing, and consumer products. And I'm sure the list is not complete, but I just want to give you an idea of the breadth that we cover. In order to manage such a diverse portfolio and to seek opportunities with the proper skills, the venture capital partners and associates of the firm are grouped into units that specialize in certain industrial sectors in order to ensure proper focus and the attention needed by a small venture capital group. For example, in our firm, Nissan Buri and myself are the two partners responsible for the HighTech electronics investments. The size of our investments range from $100,000 seed financings through $1 to $5 million on the first or second round financing of a startup, into tens of millions of dollars for corporate restructuring and management buyouts. Some examples of our investments will give you an idea of the work that we do. In medical, in the biotechnology area, we have been involved in Synergen, Vestar, U.S. Healthcare. Communications, Bridge Communications, Lycom, which is a new company in synchronous transmission. Integrated Circuit, Wafer Scale Integration is a company that we were early investors in. Software Services, Certified Collateral Corporation. And in major public companies, we have or have held positions on Mattel, Allied Supermarkets, Scotts Forsman, and now we are negotiating for the purchase of Computerland. We are long-term investors, and we work very closely with our portfolio companies to build value. We are not passive investors, and that is one of the, we believe, will bring a great deal to our companies in helping their development. Let me go on into the Hypris story, and I'll make that very brief in the spirit of the shortened presentations. In 1983, Sadiq Faris approached Warwick Pincus with the concept of forming a venture to commercialize products based on Josephson junction technology. This was not, at that point, a well-formulated plan. It was an early idea. After an initial review by the partners of the firm and outside consultants and the decision that a potential existed for an investment, the firm committed seed capital for the preparation of a business plan. And of course, at that time, Faris had resigned from IBM and was doing this on a full-time basis using our offices in New York. Chris Brody, Will Miller, and myself worked very closely with Sadiq in order to produce a business plan, which then formed the basis of going forward into the first stage investment. And at that time, we adopted a strategy which has continued to guide the development of Hypris since that time. And let me briefly outline it because it's important to the story that evolves. First, we decided to select a commercial product with a significant market potential that uses the unique technological advantage of superconducting electronics. That was not easy to find, but we did focus in on some products in the test and instrumentation area. Careful market research was done, even at an early stage, to specify the market and to lead to product definition, which would only be done after the market had been scoped. We decided to start with small-scale Josephson junction applications, that is, those using relatively few devices, and only increase the complexity as the technology would allow and the market needs would justify. That is, make things that fall within the grasp of the technology, not too great a stretch. Then we introduced very careful technology milestones. Since we did not know how quickly some of those major problems could be overcome, we put very careful milestones. Don't get ahead of yourself. Don't overinvest in things that are not necessary until you go from step A to step B. That's one way to minimize the investment for maximum return. We also decided at that point to seek external R&D funding from government and other sources to supplement venture capital. But obviously, we would only do that if the programs that would be funded would be consistent with the corporate product objectives. Well, we launched Hypers in July 1983, and everything went great until a bombshell hit the world. IBM announced in September that they were getting out of the Josephson Junction computer. Shortly thereafter, this was followed by Sperry and AT&T deciding to cut back, and this was not very good news for anyone. But we decided to view that as an opportunity. We had no reason to believe we were not going to go into computers, initially at least, and we looked at this as an opportunity to proceed with less competition from the big guys. And as the company proceeded in 1984, in 1985, the company put its technology in place and focused on overcoming those problems which were known to have plagued IBM and others. Reliability of the devices had been known to be a problem. Reproducibility, that is, the ability to manufacture something that you could put into a product because it had predictable cost and performance. And the company also received its first government technology development contract in late 1983 and began to form a partnership with the people in the defense and the space community that were seeking devices based on superconductivity but could not find a capable organization to provide it. And I'd like to note the work of Edgar Adelson, Dr. Fernand Bedard, and Marty Nissenov, who were some key people who kept the faith during the very dark periods when nobody believed in superconductivity and ensured that the work was continued at Hypers and other organizations as well, although the amount of funding was unfortunately very small. And in 1985 and 1986, the company built a reliable and reproducible niobium and niobium nitride technology and established a pilot line and chip manufacturing foundry that was ready to serve both defense contractors and outsiders who required it, as well as to provide the products, the chips for its own instrument products. During that time, of course, we at Warwick Pincus worked very closely with the company in staff management, technology definition, market analysis, whatever was necessary, both the monthly meetings, obviously, board meetings, executive committee meetings, but much more frequent interactions on that, days at a time spent on working through problems with the company. In 1987, the product which had been defined, which was a sampling oscilloscope and time domain reflectometer, with specifications that said the device had to operate the sub-10 picosecond speed range with some other features which we will go into, was finally ready. And it was a long development cycle, but remember that you had to build a team, and you certainly had to do a lot of technology development on the chips. A lot of pioneering things were necessary in order to make it work, and the company is building up what we believe to be a very attractive portfolio of patents based on the work that it's been doing, and these are in various stages of either having been filed or being filed, and that will be an important asset of Hypers. And under government contract funding, although the government contract funding never paid for all of the work that had been done, but it was done because we believed to be important for the future of the company, we have developed at Hypers a niobium nitride technology, and a digital squid will be ready this year, which we believe to be a very important product for the future. So the company introduced its product, as I said, in 1987, and it was installed in various customer facilities, and the results to date have been very encouraging. The product is reliable and meets specifications, and it has been tested by customers. That's very important. And it has proven that J&J technology can be deployed in a normal industrial environment and really work and do the job that it was intended to do. And I think the company and all of us are very proud of that particular accomplishment. Now let's go on. What do the new materials mean, and how do you fold these revolutionary materials into Hypers? Well, the way we do it is in a step-by-step basis. Hypers is already active in the field and will continue to work very closely with government agencies and others. These materials are obviously not ready for product deployment or even devices that would be used in any of the Hypers products that are being contemplated. But we believe that as they do evolve, the company's basis in commercializing niobium and niobium nitride will provide a very valuable basis to build on for other products and other materials which will come out of that. Now, let me summarize some of the key things that we have learned from this experience. It's been a long trip, starting in 1983 to now. First, it is possible to fund product development in a startup and build a company. But you have to be very careful, and the strategy has to be well defined. First, clear-cut product need and product definition, and something that really makes the difference. It is not just a me-too product. Careful milestones for development. Building a management team to carry technology from the laboratory to the market. Close association with users in government and industry. But finally, deep pockets. Venture capital is needed in this particular instance. This was a major funding source, some government support. And you can't, products of this nature and these kind of leading edge technologies, very tough to predict how long it's going to cost, how long it's going to take, and how much it's going to cost to really build a successful company. And one must have the resources to continue the investment process until such a time as complete viability of a corporation is achieved.
Thank you very much, Henry. I might point out that it's not only important to have deep pockets, but also long arms as well. Eric, as I mentioned, is involved as an entrepreneur in a company in the superconductivity field, low-temperature superconductivity.
Okay. Supercon Inc. This one work? Oh, sorry. Okay. Supercon Inc., the company which I represent here, is one of the oldest, if not the oldest, surviving company in the world that's been, whose efforts have been continuously devoted to the manufacture of superconducting materials. And by superconducting materials here, I mean wire and cable primarily. We've not been concerned with superconducting electronics. We don't make magnets, but we have made the materials used in those magnets for 25 years. We're a very small company, but we're kind of outstanding in the fact that we're still around. And we have made a profit for most of that time, albeit a small profit at some times. We've seen the giants enter this business, and we've seen the giants leave, and we've seen an awful lot of small businesses founder. Our competition is worldwide. We compete with Hitachi, Furukawa, and Vacuum Schmelzer, which is a division of Siemens. We also supply Siemens, and we also supply Hitachi for the more sophisticated products that they require. It's easy in this business, I think, and particularly in this heady environment around here, to get carried away by the glamour and the excitement of superconductivity. John said this morning it's a disease, and be careful it doesn't kill you or your business. Superconductors, I think we must remember, are not going to be accepted in the marketplace just because we as young engineers, or not so young engineers, dreamed about them. Dreaming is okay, but let's be sure it's not a nightmare. To be accepted in the real world, these new materials have to be the cheapest and or the most reliable way of accomplishing something that is already being done in other ways. Or they must accomplish something that can't be done in other ways. And if they do that, it's something that needs to be done. And I think here is the key word, needs to be done, because opinions differ on what needs to be done. Depends on the political environment and the general feeling in the country at the time. And that, I think, is what's most exciting about this meeting here, because I feel that now that the administration, from the president and the secretary downwards, and hopefully the people of the United States, have suddenly realized, well, the administration has backed the programs, and the people, I hope, have suddenly realized that science is interesting again. I think now that this has happened, there may be more things that we need to know, and I think this is important. Okay, let's look at what the market's been. I'm going to leave aside the commercial market for the moment because the only commercial market of any significance that has been the MRI market, which I'm sure has been fairly well covered already. But I'd like to talk a little bit about the government market, because the government has been our main customer, and the Department of Energy, in the form of high energy physics and magnetic fusion energy, has kept this business alive for 20 years. We've worked together, and the culmination of years of magnet and conductor development has resulted in the Fermi National Accelerator Lab, Tevatron, and also the mirror fusion test facility at Lawrence Livermore Laboratory, and the large coil projects at Oak Ridge. Some of these have been talked about, and you've seen these enormous great magnets that have resulted from this cooperation. The Tevatron, which is the most powerful accelerator in existence today, is now the prototype. It's really the only superconducting magnet accelerator around, and it's the prototype for the future particle accelerators, the biggest of which is the superconducting super collider. And I think you've heard the interest that the administration has in that machine. We're very proud of our contribution to that machine. A few years ago, I think a lot of knowledgeable people in this country would have told you that perhaps the Japanese had the leadership in niobium titanium fine multifilamentary material. And I think you heard yesterday that the Europeans still believe they have the lead. Well, I contend that neither of them have the lead. I believe the lead is in the United States. I'm just going to put this one on the screen. You won't be able to see anything but a big hexagon and a hole in the middle, and I won't bother describing because I don't have enough time. But there are 11,000 filaments there, and I can elaborate that if you like. There's a lot of other things there. I think the important thing about that is that it has resulted from doing exactly what we've been told to do here. In other words, a cooperation between industry, the government, and the universities. Twice a year, we all meet either in the snows of Wisconsin or the palmy beaches of California, and we talk about the problems involved in developing that conductor. We've done that for 4 years, and I think it's been very profitable collaboration. So I think if we can continue cooperations of that nature, I believe that we can keep leadership not only in the conventional niobium titanium superconductors, but also the leadership we have in the high TC materials in these United States. Thank you.
The next panelist is both an entrepreneur and a venture capitalist, Carl Rossner.
Well, actually, I'm pleased to be here because I can talk out of several sides of my mouth, because I've experienced in a number of venture and entrepreneurial environments. The first experience I had actually was at General Electric, being an intrapreneur. GE didn't quite know what to do with superconductivity in the late 70s, in the late 60s, I'm sorry, in early 70s. We began a market study, and the conclusion was that this superconductivity was at least 10 years away from commercialization. And why don't we have somebody go out into the company, act as an intrapreneur, but do it in a garage shop type mode? In other words, we're not going to give them any money. And I think as after a year or two of that, as you can well imagine, the kind of frustrating experience that was, we came to an amicable agreement that GE was willing to allow us to establish an entrepreneurial organization outside of the General Electric company, and in fact generously gave us the equipment, the patent portfolio, because there was never any hint or expectation that superconductivity would amount to much. And the thought was, well, if it really amounts to something, we just buy it back. The start that we had, of course, was again no financing, but we were able to manage a very neat trick. Since GE decided that we owed them some money for being let go outside the company with some of the equipment, we gave them a note, but also they retained initially 45% of the company. when we marched into a bank with a 45% General Electric partner, they thought they were lending money to General Electric Company. And so it was relatively easy to get the loan. It was a little bit harder to pay that loan back, but we managed, in spite of the bank's doubts when I found out that in fact General Electric wasn't going to be responsible for the money that lent us. They said tough luck to these guys when one of the bank managers called up and wanted to find out if GE was really standing behind the loan. However, I think as this meeting enters its final session, it may be appropriate to ask us who represent small business and you who represent the financial community, how can we capitalize now on one of the most astonishing scientific breakthroughs in recent history, high-temperature superconductivity? And of course, high-temperature superconductivity, to those of us that have been in this field for the last 25 years, represents just a continuum and no real change. It's just replacing one type of material with another type of material, and to have fun in an environment that literally spells magic from day one, in that it allows us to do the near impossibility of having perpetual motion machines in electrical devices. And you know how pervasive magnets and electric currents and the applications are in our lives. So those of us that have been bitten by the bug are just thrilled that after having committed ourselves to this technology 25 years ago, the real applications will come, and this will in fact be recognized not only by ourselves as pioneers, but also by the rest of the world. In fact, the importance of this event goes beyond a specific call of action for action, because U.S. industry and society at large at this point, however, are caught in the increasing internationalization of science and commerce to a point where our ability to compete in manufacturing especially is seriously questioned by many around the world, and in fact by many of the large U.S. companies in this country. I have a few slides just to show you an overview of our company and a few review graphs after that. If I could have the push button there as well. I think you have it there. Thank you. Let's see.
Oh, you don't need this?
Yeah, I need that as well. Well, let's see. I may not need it. Let me just. Maybe well,
we didn't rehearse this.
I don't know whether you can see any of this. Okay. I guess the lights are a little bit too bright. But anyway, this just shows the continuum that I was talking about. And in fact, there have been several ups and downs. A real breakthrough similar to the one that occurs today, in fact, occurred in 1961, where the electrical industry in particular was caught up in the excitement. The easy work was done in 2 or 3 years, and then people found out it was very tough to, in fact, get real commercial application. And that's what led to, of course, the spin-off that we experienced and the kind of spin-off that High Press ultimately experienced as well. Here's just an overview of our company. We were founded in 71, but rather than limiting ourselves to just superconducting materials, we, in fact, developed the expertise not only in materials, but also magnets, research system, magnetic separation system, the cryogenic requirements that go with it through some recent acquisition, and the electronic accessory equipment. We have now grown to a company of 300 employees, in fact have locations in 4 states in the United States, and have a European joint venture with one of the largest electric equipment companies in Europe, Alstom in France. We have, however, benefited very significantly by the availability of venture capital. And that has allowed us to become the first publicly owned company in superconductivity in 1981. We have gone back to the marketplace 3 times after that, have raised a total of $33 million, and that has allowed us to become what many people consider to be the most successful superconductor company in the field to date. And we expect, obviously, to continue being that, in that our perspective is that superconductivity will, in fact, become a major industry, and we expect to be at the forefront of that technology. I think I skipped a few of the slides just to show the application in many, many technological areas. We have delivered magnets to all of these and collaborated with many of these to bring products to the marketplace, typically one of a kind, until 1981, when magnetic resonance appeared, and that is really the first commercial application for superconductivity. Secretary Harrington this morning indicated that roughly $100 million was being spent. He probably meant $100 million a year in superconductivity. However, we have actually in total have revenue of $100 million over our 15 or 16 years experience. Here's a sample of a conductor again, a sample of a tape and various types of conductors that you manufacture in various shapes and sizes. These superconductors can in fact be made into any shape, carry any current that you wish. We have also entered the field of systems technology. Since superconductors cannot work by themselves, you have to have them in magnets and subsequently in systems. So we have developed an interdisciplinary capability in both electronics, cryogenics, superconductivity, and magnetism. This is what a typical MR magnet looks like. I think you've seen it many times. This is what a truck looks like. We pioneered the placing of magnetic resonance magnets onto moving trucks so that the cost sharing that was forced on many hospitals, the financial crunch that the hospitals experienced, could in fact be covered by having a truck move between different hospitals. These are just several images. Skip over those. Questions typically arise, why do you need superconducting magnets? And it's really a question of economics. I think that is in fact what everything comes down to into a successful business after all. The bottom line is, can you make money on it? Can you sell at a profit, and can you be profitable? It turns out that both resistive magnets, superconducting magnets, and permanent magnets have been tried for inclusion into magnetic resonance systems imaging. And it turns out that while permanent magnets seem to be very attractive, you seem to be able to get something for nothing, unfortunately permanent magnets are limited to relatively low fields, and that when you want to go to high fields, especially anything above 0.3 Tesla or so, you have to go to superconducting magnets, and that's of course what makes superconductivity so exciting. Here just an example of sizes of a permanent magnet versus a superconducting magnet. Permanent magnets do have some attractive features, and ultimately I think will find a niche in the marketplace. And we have just recently purchased a permanent magnet company as well, so that we can be broadly in the marketplace of both superconducting magnets and permanent magnets. We also, this is just a view of our wire drawing facility. We have about a 45,000 square foot plant. We are fortunate in filling this plant with multi-million-dollar orders in that we are supplying several of the magnetic resonance imaging magnet companies with wire to build their magnets. This is a view of our factory making magnets. Here's a view of our spectroscopy system. This is the eggs story that some of you may have heard this morning. We actually had an experiment where we watched the growth of a chick inside the eggshell, just to indicate what superconducting magnets in conjunction with magnetic resonance can really do. We also developed a spectroscopy system that's now available. Finally, a few more slides on the cryogenic requirements, and of course this is where the new superconducting technology will make it a lot easier to keep these things cold and in fact reduce the complexity of the cryogenic equipment. That is a major saving between what we call conventional or low temperature superconductors now and the higher temperatures superconductivity that we hope will come on the scene within the next 5 to 10 years. Here are some questions. What is the optimum field strength? Can room temperature inexpensive magnets, and I emphasize the cost aspect of this, be made, because the room temperature technology will only succeed, of course, if it is cost effective. And what are other broad medical applications that one can use? Here's just a picture of what the Japanese have done. They have really carried the application of superconductive technology to an incredible level. They have literally poured almost $500 million into an experimental levitated train project using superconducting magnets. If you could see it, you see a conventional train on the left and a superconducting train full size on the right on a 10-kilometer test track. When you stand next to it, there's a remarkable difference between, I was invited to an experimental run of this train in Japan several years ago, and you hear the clickety-clack of the regular train going very slowly, and you see the superconducting train swooshing along at 3 or 4 times the speed, roughly 500 or 300 miles an hour, 500 kilometers an hour, and there's remarkably absence of noise, and it just really is an experience that you see, gee, this is the future, and the future is now. I have a few more slides, a few more view graphs, just to go back to the venture capital aspects of this technology. I'm trying to contrast what I think are the key success factors in different kinds of technologies and industries. In the consumer product areas, it's very straightforward and easy. In real estate, there's only one success criterion, and that's location. When you come to success factors, however, in high tech, and as you can see, I put 2 or 3 very important ingredients on top. First of all, the long-term view. And unfortunately, that has been missing from a large part of U.S. industry and U.S. society. We all are tremendously impressed by the quick buck artists who promise you the moon tomorrow. When you talk high technology, it's a rare company that overnight or within a year or two can, in fact, return your money tenfold or 100-fold. And it's still possible, of course, to do that by starting small high-tech companies, but the going gets rough after that. Money, obviously, there's never enough of it. And I think the Genentech approach is, in fact, what I would certainly recommend to most high-tech companies. Get as much money up front as you can get, because you sure need it, and try to find a way to go back to the marketplace. But perhaps more important even than that is that good high-quality management and a high-quality management team is probably the most important ingredient in any successful high-tech company, because any small company or medium-sized company or large company needs the same kind of ingredients, and that is management that understands finance, that understands marketing, that understands the technology, that is politically skilled in negotiating with customers' agreements, working with the government, and so forth, so that you have to really make sure that all the areas are covered and covered just as well as a large company. And that is what makes life in a small company so exciting, but also so difficult. And of course, you have to have a market, have to have marketable products, that's understood. Capable and loyal employees. You can't have a turnover every year and lose some of your key employees and have to search for them, because especially if you live outside of a metropolitan area, it's very often very difficult to find the right kind of skills and people. Patents, in the first 10 or 12 years of our company's existence, we didn't file for a single patent. That has changed in the last few years, because my perspective was that unless you're willing to put enough money aside to defend a patent against infringement on the order of $100,000 or $200,000, and if that was a criterion as to whether a patent was worth filing for or not. And in my opinion, we didn't come up with a good enough idea to put $100,000 or $200,000 aside, and in fact we didn't have it. So now, fortunately, we're in a little bit better position. In fact, it's easier to get patents, and patents are more meaningful. So our tune has changed on that score. And of course, you need quality control in your products, and last but not least, excellent financial controls. Next, final slide is really just to show you the mountains that one has to scale in terms of the various phases of the development of a high-tech product until you've hit the final mountain where you can slide down with a big payoff and make a real profit. In that the basic R&D is certainly only the first step. The period of discovery and invention takes some money, but not nearly as much as, in fact, the next step, which is a most difficult one, and that is to make that transition from the laboratory into a factory and a commercialization of the product, and ultimately, of course, to convince your customers that you have a product that he should buy not only once, but continuously buying. And I hope that this chart will sort of set the stage for some of our discussions. Thank you.
Thank you, Carl. What we've done so far is talk about what you might call more traditional styles of venture capital, investment by venture capital firms into young companies. Our next speaker, Paul Kaminski, will be talking about corporate partnering as a vehicle for funding the research and development and application in this field. Paul?
Thank you. I'd like to talk just in 3 short parts. One, I'd like to look at a case history to begin with, looking at the development of the transistor and its transition into the integrated circuit, and draw from that some lessons learned about the evolutionary and the revolutionary nature of the technology development as well as the market development. And I think there's some lessons to be drawn here in high-temperature superconductivity, and then go into the third piece, which is look at some financial arrangements and problem way back then was that we didn't have materials of sufficient purity to be able to realize devices of interest. By the 40s, though, sufficient foundation for the study of semiconductors began to emerge in Bell Labs. They had, by that time, produced crystals of sufficient purity in both silicon and germanium to be of interest, and had begun doping those crystals. In 46, Shockley began an experiment based on his calculations to look at electronic amplification. Those early experiments were very negative. Results he saw were a couple of orders of magnitude smaller than what he predicted. But he continued for 2 years, developing the first transistor action in 47. What was revolutionary there really was not the material base at the time, but the injection of minority carriers, which were used to enable and control amplification. The process I've described there, I would describe as a fairly revolutionary process in the development of the technology. But the large companies who were supporting the research and the application, I conclude, had in large measure an evolutionary market approach. The transistor was thought of as a replacement device for the vacuum tube. Now, it's kind of interesting for me to contrast with that, the development of the integrated circuit. I'll start here in 1952. At a conference not unlike this one, a gentleman from Great Britain, G.W.A. Dummer, really forecasted the process leading to integrated circuits. I quote from the presentation he made here in Washington, D.C. in 52. With the advent of the transistor and work in semiconductors generally, it seems now possible to envision electronic equipment in a solid block with no layers of insulating, conducting, rectifying, and amplifying materials. The electrical functions being connected directly by cutting out areas of the various layers. It's hard for me to follow exactly what happened in the UK, but in 1957, the Royal Radar Establishment actually placed a contract to develop an integrated circuit. Now, what Dummer in 52 had called his peep into the future was interesting, was actually realized in 58, not built in England, but built in the US. Kilby at TI was credited with first conceiving and constructing the first working device. Bob Noyce, who Ed referred to earlier, one of the 8 founders of Fairchild, credited for the sophistication of bringing that device into specialized use. Now, what was interesting in that case here is Dummer, now semi-retired, reminiscing about his experiences and the outcome. And again, I quote from him. It's worth remembering that the giant American electronic companies, with few exceptions, were formed since the war by relatively few enterprising electronics engineers setting up on their own with either their own capital or risk capital from a bank. Often a government contract would start them off. Hard work was necessary, and the large home market was a great asset. The climate of innovation was such that any advanced technical product could be sold. The American system of encouraging employees to hold shares in their company is one which should be emulated, as a part share in the firm's prosperity gives a sense of increased responsibility. Successful businesses are almost always dependent upon a few people who are innovative and enthusiasts. Now, as I think about a model for the integrated circuit development, here was a case where there was a prediction of the technology to be developed. And I would probably sell things short if I called it completely evolutionary. There certainly were some revolutionary steps, but the process was understood. There was a lot of logical order to be pursued. What was not a logical order there was looking at the market. Very few of the large companies really were willing to take the revolutionary steps in looking at the market. As I said earlier, the thought process was looking at the transistor as replacement for the vacuum tube. It was the small company environment that stepped up to take the risks and to look at entirely new applications which at the time were already thought of in looking at a revolutionary marketing approach. As I think of these two, I believe there's a little bit of a model there to be followed as we look at high temperature superconductivity. There is a need, there's a resource base in large companies to do both evolutionary and revolutionary research to look at what will often be evolutionary market applications. There's also a real environment, a set of risks, rewards, and great flexibility in the small company environment to look at, again, both evolutionary and revolutionary technology, but with a greater focus on revolutionary, today unthought of market applications. great flexibility associated with a small company in pursuit of that activity is simultaneously a great benefit and also potential for disaster. Small companies can move very quickly in pursuing ideas in a revolutionary way, but that nimbleness and speed can also lead to great problems in a very short period of time. When you think about financial arrangements in this situation, I want to constrain my remarks principally to one activity, which is the strategic partnership idea, which is becoming developed. If I look at that same model again, and look at a small, very nimble company, which is taking advantage of research and perhaps looking at a more distant market application, which is a revolutionary market application, there are from time to time situations where a large company interested in an evolutionary application of that same technology can benefit by injecting that technology into their own operation. The benefits from that kind of an association can be very substantial if the right conditions exist. A small startup company very often has very difficult times dealing with market entry barriers. Becoming recognized as a company, being able to develop a product and getting somebody to buy it. In a relationship like this, if a large company has a market opportunity available, has an evolutionary plan in mind where an external technology can be injected, this kind of a partnership has a way of putting a small company on the map, giving them a market to work into, giving them a raise on debt early in the process. That market that they're working into with a large company is a market that's orthogonal in some sense from the eventual market which they wish to pursue. Then there may be a happy circumstance, as they can support a market application of interest to a large company. In fact, an interest which is expressed by the large company in the form of R&D funding to develop that technology. And it can be a very beneficial situation for the large company to not have everything depend on that, to have an external window of what's going on, but just to have this as an alternative. And all the better if success in the large company's market is a necessary condition for success for the small company in their own eventual market downstream. Now, it isn't always possible to structure relationships like this. One has to understand the underlying technology, how it may fit in both the evolutionary and the revolutionary market situation. But it's a situation that I think we in the U.S. can take great advantage of because of the very unique small company environment that we have, an environment which really is not reproduced to nearly the same degree in Europe or hardly reproduced at all in Japan. So one of the efforts that I and my company have been working at for the past couple of years is in the development of these sorts of R&D relationships between large and small companies. They're relationships which are fundamentally research and development in nature. They often involve, as a sort of strategic sweetener, some type of minority equity investment. But that is an after-the-fact element. The fundamental relationship that has to be structured is the underlying research and development relationship. I don't believe that model is a model in which all or perhaps even the primary method of financing will occur in high-temperature superconductivity, but I believe it is a path which will be an interesting path for many applications. One other comment to be thought about in this situation, which is thinking just for a moment from the large company side of things, whereas the strategic partnership relations can provide to a large company an external source of ideas, a window on technology that they themselves may not be willing to invest large amounts of internal resources in. There's another model which I think we're seeing a foundation developed for in the U.S., the consortium model, where in places the revolutionary research that needs to be carried on in a beginning applied sense, a step or so removed from product development, but also a step further downstream from underlying basic research, especially in applications where a large capital base is required. There may be, and perhaps in this case is an opportunity, for one or more research consortia to support the development of that sort of shared transition research among large companies. Just to wrap up, this whole idea of strategic partnerships is an idea which is new, It involves the ability to inject both evolutionary and revolutionary research into more evolutionary market applications for large companies, but provides a basis for small companies to develop revolutionary market applications in the longer run. It's a set of relationships which involve R&D and potential for equity financing to have two companies form a strategic long-term relationship. It's a relationship which very often is not appropriate for seed startup financing of small companies, but more appropriate in first, second, perhaps even third round financing prior to public offering stages.
Thank you very much, Paul. Those of you who read the Wall Street Journal this morning got a head start on the next presentation. There was a description of some of the aspects of the formation of American Superconductivity Corporation, or Superconductor Corporation, that John Preston was involved in as Director of Technology Licensing at MIT. John?
I'm lucky. This was totally unplanned already. This is the second time in a row that the Wall Street Journal has published an article on something that we've done on the day I have to give a talk. So I must be living right. I'm Director of the Technology Licensing Office at MIT, and what that means is that we handle all of the inventions coming out of MIT, Lincoln Laboratory, and the Whitehead Institute, which is about a $600 million research base. I get about 2 invention disclosures in my office each day, and we file on about 3 patents a week. And we conclude successfully about 1 or 2 license agreements per week. And typically they involve about two inventions per license agreement. About 6 times a year we come across a technology that we think is really good for creating a new business. So we're averaging about 5 or 6 new company formations out of our office. It's probably a drop in the bucket relative to the spin-off companies from MIT, but in terms of those that have intellectual property associated with it, I think we're capturing all of them. About 5 years ago, you would never have seen a university administrator sitting up here because, quite frankly, university patent administrators were, in my opinion, black holes for inventions. Inventions went into them, and licenses never came out, and new startups never came out. There was a strong bias toward licensing only large existing companies because it was safer. We're sort of treading new ground at MIT. Licensing startup companies, there are all kinds of potential conflicts of interest that you run into, where when the university owns equity in the company, the professor owns equity in the company, we worry that our students will say, wait, am I doing research for my educational purposes, or am I doing product development for my professor's company? Rather than skirt the issue, we decided to just address it straight on and look at conflict of interest straight on and manage it. The impetus for change at MIT came in part from the government. The presidential order of April 10th that you heard about, Public Law 96-517, the Bayh-Dole bill, giving contractors stronger ownership on the technology developed at the universities or at small companies now, or large companies, any U.S. contractor. Those 2 bills, the bill and the presidential order, were really a response to a need to improve our international competitiveness. The Japanese are doing a good job at developing technology, and perhaps in some areas a better job than we are. As part of the reorganization in terms of looking at how to manage intellectual property and license inventions, MIT reorganized its patent office. We changed from a legal orientation. We had patent attorneys running the office to now we've got entrepreneurs. Before coming back to MIT, I had started a MIT spin-off company that's doing fairly well, and got my arm twisted to come back. So I'm a former entrepreneur. I've been involved in about 9 startup companies, and as a consultant or co-founder of 2 of them. So MIT wanted someone who had successfully taken technology out of MIT to manage the technology licensing operation, because they figured a former entrepreneur, a technology-trained entrepreneur, would understand a little bit better what it means to transfer technology. Because of time, I want to leave some time for questions. I'm just going to make a couple of very quick comments about universities in general. U.S. universities control about $10 billion worth of government research money, $6 billion directly to them, and about another $4 billion at university-controlled research laboratories like Lincoln Lab, which MIT runs for the Department of Defense, for the Air Force and Navy. From all of that $10 billion worth of research, universities, according to my back-of-the-envelope calculations, get about $30 million in royalty income per year. As a former entrepreneur, I could go to one of my venture capitalists and say, give me $10 million a year, and I'll skim off the best intellectual property from some sucker who's putting $10 billion into this research. And in fact, perhaps the Japanese are doing a little bit of that right now. The point there is that getting intellectual property from universities is cheap, but that's the beginning of the story. Finding people who can develop that technology into meaningful business is a really tough part. And what we've done at MIT in terms of startup companies is we've found a dozen or so venture capital firms who have the ability to build businesses from a zero stage up. In fact, a friend of mine who's president of Zero Stage Capital calls our deals a -2 stage deal. And I think that's right. We have no entrepreneur typically. Income to universities. I think between Stanford and MIT, we account for about a third of it. Stanford has a very successful program, and it's been more successful than MIT's over the past. I've only been at MIT for a year, and so I'm looking forward to a good competition with them. By the way, during our first year, after changing from this legal orientation to a business, marketing, and entrepreneurial orientation, we've gone from about 12 license agreements per year to over 60. And also, we've created several new spin-off companies, which was something that never went out of the patent office before. Even though there are about 1,000 spin-off manufacturing companies from MIT, very few of them, maybe about 50, have gone through the licensing office in MIT's history. Several months ago, 2 faculty members at MIT came to me with a new concept for making high-temperature superconductors. And the concept was, let's make them usable. Let's make them ductile or flexible. And they had a real neat idea on how to do that. I see Greg Urich back there. Maybe Greg could stand up. Professor Urich is one of the 2 inventors. I don't know if John Vandersande is here. But Professors Urich and Vandersander were the 2 who approached me, and in essence, I shared their vision. I thought that if you're looking for an opportunity to create a new business, making these materials more usable was definitely the route to go. So I contacted a couple of people in the venture community. Actually, the first phone call I made was to George McKinney, who had worked with me on some previous deals. George is also here. He's acting president. George, are you back there? You want to stand up? Stand up for a second. George is acting president of American Superconductor Corporation, but his job prior to starting that was general partner of American Research and Development Corporation. So we had 4 people who were convinced that something good could happen, and George has brought in also Rothschild Ventures. I don't know if Terry Hobbs is here, but Terry is also one of the key players. Let me show you a couple of quick slides, and then I'm going to quit because we want to have some time for questions. Push the button. Yeah.
Nothing is set.
Can you go forward?
I did. Maybe backwards?
I think.
Lights on.
This is a micrograph of the material. You can see a 10 micron marker line on the bottom there. The white material that you see is gold, and the gray material that you see is the superconducting, high temperature superconducting material. The small black marks are just defects created in polishing material and getting it ready for this photograph. Those defects are not in the material when it's made. But if you can envision a sponge material where the sponge is made out of gold or some noble metal that's fairly ductile, fairly flexible, and in between the golds in the sponge you have a continuous layer or continuous superconducting material, you can see where we're going here, trying to create something where the mechanical properties are dominated by the gold, and the superconducting properties come from the high temperature superconducting material. This one is a europium-based 1,2,3 compound. If we can go to the next slide. This is the characterization of the measurement of TC. So this is the data that shows that, in fact, we do have a 94-degree turn on of TC, conversion temperature. I'm going to stop. I've got a ton of other things to say, but we're running out of time, and I want to leave some time for questions.
Thank you very much, Ron, and all the panelists. By the fiat of the chair, I'm going to describe to you the rest not only of this session, but the subsequent session. What I'd plan is that we get into a discussion now using the microphone that's there in the center of the room so that we get everything captured on the videotape and people can hear your questions and comments. We'll take a short break toward about 3:10, very short. And then rather than having a description from the panelists, again, we'll just continue the conversation here. Those who need to leave or want to leave to go to another meeting could go at 3:10, and those who want to stay or people who want to join us at that time can just get re-engaged in the discussion. So from this point forward, it's really up to you. Anybody who has comments or questions, I'd like you to walk to the microphone or at least have Fred Levitt here from the White House hand it to you so we can get this recorded. So start out.
I'm Lee Rudy, the Dean of Engineering at UC San Diego, and I'd like to ask John Preston. I've been involved in problems of licensing, et cetera, in a state university, a very large state university system. What hope do you think there is when you bring in a state government as a partner in this, now making it an even more complex institution?
Well, they're actually one of the most successful licensing offices. Defies all of the rules. It's the University of Wisconsin, and it's run by a lawyer. And he's doing an amazing job. It started actually with pressure from the Wisconsin alumni who said, let's create something called the Wisconsin Alumni Research Foundation and try to license intellectual property. It can be done. It's a difficult problem, and I think the fact that you're a state organization makes it slightly more complex. Being MIT, though, I think that we even have some problems that you don't have, because everything that we do in terms of potential conflicts of interest, whether they're real or perceived, gets a lot of visibility, and more visibility than almost any other university. And it's the conflicts of interest, and I stress that many of them are just perceived, that are the strongest ammunition against an effective technology transfer program in the university.
Are there any other university people here, particularly from state universities, that could shed some additional light on Professor Rudy's question? with experience? Yeah? Did you hear?
Well, with New York State, perhaps you might use the mic here. I'll bring it down.
Did you identify yourself?
Sure. My name is Paul Swartz. I'm with the New York State Science and Tech Foundation. And just coincidentally, I spent 25 years in superconductivity, but that's as an aside. What we have is a small venture capital program. And we have several $1 million that we invest in New York State high-tech startups. So far, none in high-temperature superconductivity, although we're willing to look at any that come along. But we have invested in about 25 companies in the last 3 years, both debt and equity.
Is that money from the state?
Yes. Yeah.
So this is an example of where the state government has gotten actively involved in providing funds to help start companies and fund their growth.
That's correct.
Other comments? Yes, sir.
I have a couple of questions for the panelists. My name is Vijay Kapoor. I'm from a small company in California, named the company is ISET. I have a question for Paul Kaminski. I'd like to know what is the time factor involved in setting up this corporate partnership. I'm told it usually takes more than a year, year and a half.
I would say from experience, it always takes longer than you thought it was going to take. And the feel for the timing, 3 to 6 months are not unreasonable time frames to look at. But I would say experience says if I were to pick a single number, it would be in the range of about 6 months. From first discussions to actual negotiated, agreed, and closed strategic partnership.
It still is a long time.
Yes, it is.
What should let's suppose there's people from small companies that are interested in finding ways to work with larger companies. What would you suggest, Paul, based on your experience, that they do as a first step?
The difficulty really is starting to focus your efforts and pick the right company to begin with. And that's the most important advice I can provide, because large companies have so many resources. There can be so many meetings involved. Those resources, those needs are very draining on small companies. And many times large companies don't realize what a drain it is just to be supporting meetings and visits. And so trying to do that with many companies in parallel at the same time.
Does your company suggest the name of large corporation, or should the small business come with it, a name of a large corporation that they would like to go together with?
When we do this work, we try to assist in that process, that is to identify what might be the best available targets.
Okay, I have another question for Dr. Kressel. You alluded a little bit onto the idea of supporting new companies that might be going into high temperature TC through the government contract work. Supposing if a small company has some new ideas and writes proposals and get a contract and wants to really move ahead, in the absence of a clear definition of a product at this stage, I can take an example of thin film coatings of this high TC. What's the mechanism of getting some kind of a support from your company?
Well, if we think that it's a question of a certain amount of time which is necessary to define a product strategy of some kind, either the product could be R&D development funded on a funded basis by outsiders, or it could be R&D which is necessary to move towards a first step product of some kind. We have in the past provided small amounts of funding we call seed financing, which is the way to get these companies off the ground. But eventually what you need to do in any kind of a startup, you need to have some strategy which tells you how you're going to finance your operations, which means some strategy which takes the company into self-sufficiency. You know, it's not tomorrow morning, but there has to be some thought given to it, and that's what the business plan is.
Well,
we will work with entrepreneurs to work towards that objective.
See, my question is more specific. Say, for example, in this, we heard a lot about thin film coatings on these high temperature TC materials. And I don't know if I have some ideas, I cannot really come up with a definition of a product. A typical venture capitalist will say, well, tell me what product definition you have and what market you're going to go into. So in the absence of that, if there's money available from the government agencies, let's say we get some money from the government agencies, but I like to move ahead aggressively, I'm not going to have a definition of a product. All I could offer you is some kind of a proprietary processing scheme. How would your company help in that? I mean, your venture capital will help in that sense.
As a general rule, venture capitalists do not support basic research.
Well, I thought you mentioned something early on in your talk.
Well, what we said is that as part of Hypress's product strategy, they're actively involved in the high-TC materials area because they need to in order to ensure their future. But this company already is a going entity. It's a different story from starting out all over again and trying to define a product based on high-TC materials. Now, I'm not so sure that there may not be products whereby one can think the whole process through, and it's very possible that just a coating technology may lead to something very interesting. So, I can't give you a black and white answer what we would do in a case like this. I would sit down with them and work through the mental exercises. What could this mean? What's involved in moving to some point where self-sufficiency can be attained, or at least you have a viable business.
Next.
My name is Mark Johnson, and I work for AT&T, and I do strategic planning there. And I'd like to direct my question at Paul Kaminski. I found your idea of collaboration between entrepreneurs and large corporations very intriguing. And we've heard a lot the last few days about applications of high-temperature superconductors. And I'm wondering where you believe the first applications of these high-temperature superconductors are going to come into play in terms of entrepreneurial startups. We've already heard of a few here, Hypress and American Superconductor. Do any other areas pop into your mind where applications might occur?
I'm sure there are as many ideas here of what happens first as there are people in the room. My own biases are that I see much work that was done in preparation for superconducting devices prior to the recent achievements in high TC. And so a foundation was laid for microelectronic applications, which I see as near term. So the short answer to your question, I see actually the environment for products to be in the marketplace, perhaps within a period of 2 to 3 years in various electronic applications, in particular very high-end, high-performance applications, the kind of applications in which you cannot ignore between 2 and 4 orders of magnitude in switching speed and energy dissipation product. So I view that as an area where we'll see near-term products to be developed. Certainly, a whole set of related applications, many of which are not well defined today, dealing with the application of magnetic devices, superconducting magnets, and related higher sensitivity sensing devices, the combination of squids I can see and the more intense fields that are available at lower cost. So in general, the conclusion I would draw is that I see the nearest term applications where we're seeing very enormous performance advancements to provide new capabilities. I see generally longer time periods being required for the cost reduction applications, especially those involving substantial infrastructure changes.
This is a really important question. Are there other people on the panel that either argue with what Paul says or want to add to it?
I'd particularly...
what are the first applications? What should we be focusing on?
I'd like to hear what Dr. Kressel thinks of that, especially since he's already been involved with Hypress. He's one for one already. I'd like to hear what he might think.
I can only tell you we spent a lot of time looking into the problem and tracking very carefully what's going on in these developments. At this point, what we think, and I know Sonny will have to speak for himself, but I think we agree on this score, is that the state of the materials as currently available, what we know now, it is difficult to postulate a useful embodiment in something which is of, let's say, of a product basis. However, that does not mean that you don't look at those things. And supposing problem A is solved, and we can go into a lot of details what that would be, or problem B, what does that mean to what? And we have worked out, at Warwick Pincus, as a matter of fact, a matrix, which tells us which areas would be of interest if certain problems were solved, and then we would perhaps begin to focus our attentions as products into those areas. But it's really premature to execute any of that because the technology is just too new.
Thank you very much.
I think it might be useful to comment on that question. If you have listened to all of the speakers in the last few days, you have found that the field can basically be broken down into electronics applications such as small circuitry or small current applications, and large-scale devices and large-scale applications. It appears, from my perspective, certainly that the early beneficiaries ought to be the electronic type applications where you need small amounts of material and presumably can make devices one of a kind that you can thoroughly test and develop. But in any situation like that, and that was also mentioned, I think, you really have to understand what the conduction mechanism is. Somebody will probably win the Nobel Prize to explain how these new superconductors really work. And until we understand the fundamentals of this and know how to make good materials, reliable materials, able to make reproducible materials, anybody's guess as to what the new applications are going to be. But I can assure you we are going to track it very, very carefully. In fact, jump into this with both of our feet, both because of the opportunity and, of course, because of the potential threat to our existing business. But on the other hand, that threat is at least 5 or 10 years off. So that gives you some perspective as to what the real world is really like.
At this time, since it's close to 3:10, what I would like to do is take 5 minutes, no more, panelists. We'll get started again. Anybody who wants to leave can do so at this time or change places, and we'll just continue where we left off at 3:15. Thank you.